It is my great pleasure to introduce Bill Randall. We've known each other for quite some time, and it turns out...
Can you say how many years?
I think we met maybe at a NASA meeting in perhaps 86,
Yeah,
something like that. So whatever that is, 40?
We were both in grade school at the time.
Yeah. Well, when we were younger, we used to hang out in Nepal together. Well, that's actually true. In 2013, I'm grateful for Greg and Archana to help me to get to this meeting. It was an ACAM meeting, and Bill was there. I remember the last day we happened to be with some people going on a tour of a place, and this guy with a big scar was with these big eyes, was giving a wild lecture about the 4 ways people around the world deal with dead bodies, and I think that's when I left. I had to go catch a plane. I guess it all worked out. This is at Patinum or something,
Okay.
with the burning guts, all the smoke, and I just sort of abandoned me there. It's like, all right, well, okay, so I think his wife grew up in Wisconsin, but Bill grew up in Iowa. He got his PhD in physics from Iowa State with John Stanford. He's now a senior scientist in the atmospheric chemistry observational and modeling division, a new name. And before that, he was section head for, he is now section head for remote sensing. Before that, he was director of ACD from 2007 to 2015. He has 150 journal articles, which I would characterize his articles and talks as amazingly lucid, just insightful and clear.
Maybe this one's going to be bad, though.
This might be an outlier. Yeah, I guess I am sort of, I found myself in admiration of his accomplishments, and I'm a bit of in his fan club, so maybe you would be too. He's a fellow of UW-AOS. I'm struck with how helpful he is with young scientists at meetings. He's always very good. Yeah, wide range of topics in observational and modeling analysis. One time you said something like, I said, well, what do you think about this? And you said, well, you should ask a real dynamicist. And I thought, are you talking about, I don't know, maybe the only person I can think of is maybe Isaac Helden that you might think of relative to your dynamic. In fact, he does have a paper with Isaac Helden on the chromaticity of critical surfaces and transient breaking in the southern hemisphere. All right, well,
I don't have much time to talk.
Yeah, okay, here we go. Fingerprints of anthropogenic influences on climate. 4 decades.
Thank you, generous man. And thank you for inviting me here, Kaiway, especially for inviting me to come here. And I had friends here and met some new friends today, but I've never been here before, so it's fun to come and visit. Okay, so this is what I'm going to talk about. Basically, I'm going to talk about temperature changes from satellites. We now have like 4 decades of satellite temperature measurements of the troposphere and stratosphere, so I'm going to talk about what they look like in terms of trends and long-term variability and changes, and how it compares to a state-of-the-art chemistry climate model. And I should say thanks to my colleagues, Fei Wu works with me at NCAR. I'm going to talk more about temperature trends, colleagues, during the talk, you'll see, and then the WACCM group, and Doug Kinnison particularly, who helped with these simulations. Okay, just a brief overview. I'm going to talk a little bit about the background of what's interesting here, I think. What I mean by fingerprints of greenhouse gases and ozone-depleting substances on the thermal structure of the atmosphere. I'm going to spend about half the talk talking about satellite data and how people make climate records and what the current state of the art is in terms of looking at long-term changes, and variability and trends, and then I'm going to, the last half is comparing the same thing with model. Okay, so this is a kind of a simple view of climate change in the stratosphere, and the simple picture is that the troposphere warms under increasing CO2 amounts and the stratosphere cools. And this picture is from the ozone assessment back in 1985, but the basic idea is, in fact, I just went and looked at this paper again. We're in Manabi and Weatherall, which is some of the first climate model simulations, including a low-resolution stratosphere, and they show this effect. And basically what's going on is in the troposphere, the optical depth of CO2 is high, As you increase CO2, you trap more radiation and you end up warming the troposphere. The stratosphere, the optical depth of CO2 is small. The stratosphere cools by radiation from CO2. If you put more CO2 in, you cool more, and the stratosphere cools. So that's the basic fingerprint of tropospheric warming and stratospheric cooling. And that's what that's one of the punchlines of the whole talk is that stratospheric cooling is much a characteristic of anthropogenic climate change as tropospheric warming is, and we'd like to understand that and quantify it. There's another curve on here of all gases, so there's additional tropospheric greenhouse gases, N2O and methane, among other things, that goes from here to here, and in the stratosphere, the other trace gases are ozone-depleting substances that take ozone away and cool the stratosphere that way. So that's kind of a cartoon view. So here's what, I'm going to show this again later on, but this is kind of a picture of the trends in atmospheric temperature from the current generation WACCM, and I'll talk about WACCM in just a second. But this is trends in kelvins per decade as a function of height and latitude. And what I just showed you in the last slide, the troposphere is warming here, and the number is like 0.2 or 0.3 kelvins per decade. It's a small number. And the stratosphere cools, cooling increases with altitude, and it gets up to about 1 Kelvin per decade up near the stratopause. And basically the patterns are kind of globally, this is happening at all latitudes to first approximation. There's also a signature in this run that included the ozone hole. The ozone went away, it got colder, and you see that in the long-term trends of the temperature. So I'm going to work my way back, and I'm going to compare this to what the observations show. Just a little bit about the model. So this is, I was talking with Kai Wei today. WACCM is part of the Community Earth System model. There's a group that works just on WACCM. It was originally designed it was a novel model at the time, but now it's part of the community model. It's a comprehensive coupled chemistry climate model. And the simulations I'm going to talk about here use observed forcings to compare to the observations. And what I mean by observed forcings, we're going to have specified sea surface temperatures. And that's a really important detail. And the result of that is that the tropospheric temperatures in general are a slave to the sea surface temperatures, and they're going to follow the observations, as you'll see very, very, very closely. And that's because of these specified SSTs. I won't talk today about free-running climate models, but they're a little bit different than this simulation. We also have changes in in the greenhouse gases, CO2, methane, nitrous oxide, chlorofluorocarbons, and ozone-depleting substances, chlorine, bromine substances. There's a whole list of them. But the idea here is, and you'll see this, is that they force the ozone in the model to behave like observed ozone. There's specified volcanic aerosols. There's a solar cycle, 11-year solar cycle imposed. There's a nudge biennial oscillation. And by nudge, at the time this model was developed, it did not have an internally generated consistent QBO. So this simulation uses the simulation's nudged just slightly to the observations, so it has a realistic QBO in it. Okay, and just for references, here are the climate forcings. So these are the greenhouse gases. I forget where I got this picture, but CO2 is a major component, and methane is the next major one, and then there's also nitrous oxide, and the CFCs and other halogens are a little bit of the greenhouse gas, end up warming the troposphere. This is the so-called ozone-depleting substances, and it's a measure or quantified in terms of equivalent effective stratospheric chlorine, EESC, and this is what the ozone folks talk about, and that was increasing rapidly, and then the Montreal Protocol and its amendments were agreed upon in the late 80s and 90s, and then this peaked about the year 2000. It's slowly going down. And as a result of this, ozone, when this was going up, ozone was going down. Ozone bottomed out about here, and now ozone is flat or slowly going up, and you'll see that as I go on. Okay, so that's the model, or that's the input to the model. Okay, so now I'm going to talk about data a little bit. So I'm going to talk about some time series that have been constructed from operational NOAA satellite measurements. And these are kind of well used in the community. Starting with the Tyros back in 1970, late 78, 79, had a series of instruments called the Stratospheric Sounding Unit, infrared measurements of the stratosphere. There are 3 separate channels. And the Microwave Sounding Unit with a number of channels measuring lower atmosphere temperature. And one note here is that all these instruments measure broad layer temperatures. They're downward-looking nadir sounders. They make lots of measurements every day. They kind of cover the globe. They're designed for weather forecasting. It's after the fact you go back, you take those data and try to make a climate record, and that's the climate record I'm going to talk about. And then starting in 1998, the Advanced Microwave Sounding Unit began to fly, and it's kind of, as its name implies, a better version of MSU, and that's still flying till today. And then people combine these data sets to try to make a longer-term climate record, and that's what I'm going to show, beginning in '79 and going till 2018. I want to note there's radiosonde measurements. They go up to about 30 kilometers, and I'll show just a brief comparison. But the availability of radiosondes is a background check or something you can compare these measurements in the lower, below 30 kilometers. You can compare the satellites and the radiosondes. You can't do that above 30 kilometers because the radiosondes can peter out. Okay, so making a climate record from these data is a very difficult problem. So this is a plot showing all the operational satellites that contribute to this climate record. And what it is equator-ward crossing time. So there's some satellites that are launched into an afternoon orbit, and some that are, morning orbit. No, that's right. Morning orbit and afternoon equator-ward crossing time orbit. These solid curves are satellites that had both an SSU and an MSU on it. These two just had an MSU on it. The last SSU stopped in 2006.
What does that stand for?
SSU is a Stratospheric Sounding Unit.
Thank you.
And if I could just go back, so the SSU has these 3 channels that measure the stratospheric temperature. And our whole left side of the climate record is going to be based on this SSU. And SSU stops here, as I said, and NOAA, the AMSU starts in 1998. There's a pretty good overlap here, but that AMSU record continues till now. What else do I want to say here? Note the drift in the equator-ward crossing times. This is not such a big deal in the troposphere. In the stratosphere, there's a big diurnal temperature, daily temperature wave. And so as you sample measurements here versus measurements 6 hours later, you see a different temperature. You need to back that out, undo that from the measurements to generate a climate record. You somehow need to stitch together these 7 different, for the SSU and for the MSU, you need to figure out how to stitch together these different data sets. It's really a difficult problem. Remember, we're looking for temperature changes like 0.2 K per decade, and trying to take operational data and try to derive that's a really difficult problem. It's been attacked by different groups for over a decade, a couple decades in terms of the MSU. And I hope I'll show you some of the difficulties here. This is just for reference. So now this is a comparison, and I just got this thanks to John Christie, but this is a analysis of lower troposphere mean layer temperatures, something like this MSU channel 2. I won't show it again, but the MSU channel 2 is this lowest one next to the ground. It's about 10 or 8 kilometers thick. It's a broad layer measurement. And this is actually the satellite time series, homogenized and put together by 2 different groups. And there's actually 3 or 4 groups that now have done this calculation, but this plot just shows 2 of them. And it compares with the same quantity from reanalysis data sets And you can see there's modern reanalysis, ERA 5 and ERA 2, and some of the older ones. And also from a set of homogenized radiosondes. Now, radiosondes, every day there's several hundred radiosondes in the globe, and you take those and try to do the same calculation for a climate data record, but they're strongly inhomogeneous. The older radiosondes are not as good as the modern radiosondes. They have strong corrections you need to apply for radiation corrections and other things. It's a very messy, complicated problem. Other groups have attacked this separately, and this is, let's see, there's 4 lines on here. This is 4 groups that have attacked that problem, trying to figure out how to homogenize. And I could somebody could give a whole different lecture just on that. It's a fascinating problem. But for the point here is that the satellite data is in reasonable agreement with these other data sets in the lower atmosphere. And part of the reason that is because we have radiosondes independent from satellites, and we can compare and contrast and figure out where there are breaks and do that problem.
Those have been offset by...
Yeah, they're offset by a degree or something. Yeah. Phew. But the bumps and wiggles match, and the trends more or less are quite reasonable agreement. And this was not the fact. If you looked at this analogous curve 10 years ago or 15 years ago, there were much bigger disagreements, especially among the satellite data. Because one group would do it and it was here, one group would do it and it's here, and they'd have to work together to figure out how to...
Do you have any comment about the disagreement with the satellites the last, say, 5-10 years? It seems like it's a growing difference.
It's the fine details are still a matter of contention among the groups, and this is one of the contendings, I guess. I have my opinion on who does it better, but in general, it used to be much bigger, the differences.
So what were the innovations that occurred that allowed these discrepancies to be?
It depends on, it's how you handle the satellite orbits, it's how you handle the calibration of the individual instruments, so that they have their own way that they calibrate, they look at deep space, and they do a worm target. There's all these details in the data, and there's a little bit of overlap between the data, so but at some point you have to make an assumption of how you handle, how you're going to stitch them together. And one group says, well, we're going to stitch them together based on this. Another group says, well, we believe this, we're going to do it this way. And those little differences build up. These are small differences, right? We're looking at, 0.2K per decade, so this is still work in progress.
Is the UAH, has it been converging toward the RSS or the other way around, or both?
For this, I think, be careful. UAH is still a little bit of an outlier. I think, in my opinion, I think the RSS and the NOAA groups maybe they agree, and maybe they're better. Am I on camera? Good. It's still a matter of research. And I mean, this is the proof's in the pudding. Look at the results, and if there are differences, maybe one's better than the other. But they all, hopefully they learn from each other and interact. Here's the same thing for the lower stratosphere channel. So this MSU channel 4. And now there's 3 curves on here, and they agree really well for the satellites. I should just point out, so there's long-term cooling a little bit in the lower stratosphere. There's very clear signals from the large volcanic eruptions. So it's Agung back here, and El Chichon and Pinatubo. And a 2-year warming of the lower stratosphere from these volcanoes. You can see some substantial differences here among these radiosonde data sets. And this is particularly the case for the older ones. And the basic problem, again, is that the way you handle radiation correction. As a balloon goes up, the sun hits it, it gets warm. How do you take that out? How do you take that signal out? And depending on how you choose to homogenize the data, you can get either these guys or those guys. It's surprising that there's even a kind of a more modern guy. These guys are kind of outliers a little bit. Okay, so that gives you a background. So again, there's quite good agreement here overall, and part of this good agreement is because this is a region of the atmosphere covered by radiosondes and satellites. So you can look at differences and play off each other. You're really looking for really small changes. So you can do that here. You go to the upper stratosphere, you can't do that, and that's what I'm going to talk a little bit about here. So this is that whole left side of the time series, I won't show it again, from 1979 to 2006 was from the stratospheric sounding unit. It's these 3 channels. So this is what the instrument looks like, and it's a pressure modulated radiometer, and it's a really clever instrument. It was designed in Oxford or something in the 1960s or something. And the deal is they have what you want to look at is a certain spectral band of CO2. It looks at CO2 emission from the atmosphere. And so what they have is, in the instrument, they have a little cell of CO2. And the instrument looks through that cell, and it has a known amount of CO2, and depending on the amount of CO2, you look at different regions of the atmosphere, basically, by looking through that cell, and then they modulate the pressure in that cell. You can derive, figure out exactly where, in altitude, where you're looking. Okay, so they made 7 of these instruments in the 1970s, and they launched one on Tyros N, and they put the other 6 in the warehouse, and the plan was, as you saw, they put one on future operational satellites. And then they go, then you have this record, and you go back and you try to put this all together into a climate record. So there's it turns out that there's important problems in doing this. Well, there's 7 separate instruments. It turns out that these cell pressures leak on orbit, and actually some of them leaked before. They leaked in the warehouse before they went into orbit. And as you change the cell pressure, you change the altitude where you're looking a little bit, and that because of the temperature gradient in the stratosphere, as you change the altitude where you're looking, you change the temperature. So you need to figure out how to undo that if you ever want to use this for climate record. The amount of CO2 in the atmosphere itself has been going up. So effectively, you're looking at a higher level all the time as the CO2 goes up. So effectively, you get a trend in temperature just because there's more CO2 in the atmosphere. I showed you the orbit's drift, and that's a big deal. You get 1 degree diurnal cycle in temperature in the stratosphere. You need to undo that. You're looking at limb measurements versus nadir, and those have different places they're looking at. And each of the satellites have a different calibration, fundamental calibration. It's a really messy problem.
So is that how you build that? All the
This is what, yeah, this is how somebody, if they know the details of this is how they look. So here's an example. This is really clever, I think. So as I said, the pressure modulator cells leak over time, causing a change in the weighting function. Now it turns out, somebody figured this out, that these leaks in the pressure cells, and there's 3 pressure cells on every instrument. So it takes turns looking through the 3 pressure cells. So it turns out that the frequency, these things are modulated, and the frequency of the cell depends on how much gas is in the cell. And so somebody figured out that you could look at the pressure, at the frequency that they measure on orbit, and you could derive how much pressure of the gas is in the cell. And then you can feed that information into a radio transfer model and figure out where the weighting function would go and what the effective temperature change is from this effect. Now this is so clever. I can't believe somebody could deduce this. But you can see, so these are all the individual instruments from the channel 3, channel 2, channel 1, and these are the temperature. And it's a big number, right? For this orange guy, it's more than a degree. So we're looking for a trend of 0.2 to 0.5, 1K per decade, and we're dealing with inhomogeneities of 1K per a few years or something.
So for the lower stratosphere graph a few slides ago, it looked like it was coming down with a couple of bumps, but then it leveled off. Is that regarded as real?
It is regarded as real, and that's the lowest stratosphere channel, and that's the microwave measurement. This is different. These are the upper level measurements. But we'll come back to that. So here's the net result. So these are the brightness temperature anomalies from these 7 SSU instruments, the upper channel. I think these are global means. Channel 3, channel 2, channel 1, before any adjustment and before they're merged. You can see these differences. The same channel would measure different things depending on the details. But So the two different groups have now attacked this problem, and this is the results from one group, the NOAA group, and you take these data and you apply all these adjustments and you get this. And it's a more homogeneous climate record. So this is basically the left-hand side of that climate record that I'll be talking about as we go on here. You can see that the adjustments they made have brought these curves together. Okay, so a little bit of interesting history of how this works. So there's two groups that have done this work. And it started out with a group from the UK Met Office. And it was led by this fellow named John Nash. So John Nash was he worked at the Met Office, but he was involved with designing and building the SSU instruments in the 1970s. And he knows all about the details of the SSU. And he made the first attempt at emerging a climate record like this, and he did it about in the 1990s. So he made the first attempt. It was kind of a little bit of ad hoc. He could compare satellites and try to get an estimate of diurnal variations, so doing this drifting orbit correction, and the calibration between satellites. So he kind of knew what to do in general, or what the problems were, and he came up with the first estimate of the homogenized time series. And then later on, this group from NOAA, led by Cheng-Ji Zhao, it's the NOAA STAR group, and he became interested in this SSU channel, and he went and revisited this calculation. And he did his own changes, and this is actually from a paper book by Zhao et al. In 2014. And he did it in a somewhat more sophisticated way, where he actually went in and he developed a radiative transfer model for the SSU, and he incorporated all these effects separately. And I think he did a very careful job. And so this is his result using that. But still, we have these two estimates of the same climate record. So I was involved with a Spark group looking at these things. And so this was when the NOAA group first came up with their data set, and it was about 2010 or 2011, we thought, well, we will just compare these two estimates, and that would be a good thing for the community. We'll show they agree and we understand the problem. And this is the result. And the result is that you get very different estimates of the climate record from the NOAA group and the UK MO group. And this is like version 1 data from each group. And the gray lines here are the background of what the climate models at the time showed, the chemistry climate model comparison. And this is Dave Thompson led a paper on this. But the point here is that, oh my gosh, what can we say about evaluating climate models? We have two sets of data, and they disagree by a lot. This is an interesting problem. It's like, I guess if you have two clocks, you never know which one is right. So this was the state of affairs for a while. But I was involved with this group. It was a WCRP Spark group. I'm just going to show a picture. It's kind of a motley crew of scientists here at one of our meetings. You may or may not. This is Adrian Simmons and Keith Shine and Diane Seidel and Dave Thompson and Leslie Gray is here. But anyway, so the important point of this meeting we had was that this guy here is Cheng-Ji. He's the Cheng-Ji Zhao from NOAA, and he got together with this guy hiding in the back there, right there. That's John Nash. And John Nash is retired, but we asked him to come. He came out of retirement. He came to this meeting and hung out with us for 3 days. And more importantly, he went off with Cheng-Ji for an afternoon, and they figured out how they could make progress, how they could improve. This is kind of different from the MSU, where you have we had 4 groups of several people in each group doing this analysis. Here we got basically 2 guys, and our whole understanding of the stratosphere is kind of related to these 2 guys. It was interesting. John Nash would come to the meeting, and all his information were on these old handwritten notebooks. He would show the handwritten notebooks on the overhead projector we had at the time. But he has this fundamental understanding of the instrument kind of more than anybody. So anyway, so they got together, time went on a little bit, and they both came up with version 2 of their data set. And this is what version 2 looks like between the two. And so the red curve is what I showed before a couple slides ago from the Zhao et al. The blue curve is the updated UKMO, and now there's much more reasonable agreement. So I think we have, the state of the art now is we understand the changes that need to be made, and we have a reasonable climate record for the upper stratosphere. Okay, the last little detail is that the SSU ends in 2006. So this is what something I've been involved with is taking some research satellite data from the MLS instrument that's been flying since 2004 and the SABRE instrument that's been flying since 2002, and they're both still going, and they make profile measurements of temperature all the way up to 70 or 80 kilometers or higher. But what we've done is that we've taken these profile measurements and integrated them and convolved them with the weighting functions from SSU and used them to extend the SSU data up till now.
Why don't you use errors?
Well, you know, we could use errors. I think we could use errors, but this maybe has a little bit better vertical resolution.
Yeah.
This has something for, SABRE is good, it's like 2 kilometer resolution. The errors is probably broader, and there's, basically it's because I know about these data and I know less about errors. Is the short answer. But we were talking today, I think errors is something we could consider, or errors and follow on. I won't talk about this. Okay, so what I have now, I'm going to show it. So now this is our observational time series. So these are global average temperature anomalies. These 3 SSU channels. They go from about, and each of them are broad. The SSUs are about 20 kilometers broad. MSUs are more like 10 kilometers thick at these altitudes. And so what we see here is the stratospheric cooling, and again, the SSU labeled SSU are merged SSU. They go to about 2006, and after that, it's this MLS data. We've done it with SABRE, and SABRE just about lays right on top of MLS. So we got the 3 upper stratosphere channels. We got kind of the lower stratosphere MSU channel 4 channel, and Matt, that's what you were saying before. This MSU 4 has been really quite flat ever since '95 or something. And then we had the 2 troposphere channels. And what you see here is a warming of the troposphere. It's a small number again. You see these bumps and wiggles, and all these bumps and wiggles, there's lots of averaging, but these are real geophysical bumps and wiggles in all these time series. These big bumps here are ENSO events. The big bumps here are the volcanoes. El Chichón and Pinatubo. You can, if you're a solar cycle aficionado, you can see the solar cycle in the upper stratosphere. And you can see, again, and trends. And if you look a little bit more, you can say, well, it looks like the trends are maybe a little bit stronger for the first part of the record than they are for the latter part of the record in the stratosphere at all.
Is that latter part in the upper, is that solar cycle as well?
There is solar cycle involved. This is kind of everything. So there is, this last solar cycle was kind of a small solar cycle, but this is coming down in the declining phase of that solar cycle. So I don't know the answer, but it's in there somewhere. So this is the same picture, but now I just superimpose some curves here so you can just see more clearly with your eye that there's like twice as strong trends the first half of the record for the latter half of the record in the upper stratosphere. And what this is attributable to, and I'll quantify this a little bit, but it's the change in the ozone. Remember I told you the chlorine was going up and then it flattened out and came down. The ozone has been responding. Ozone came down and flattened out about the year 2000 or late 90s or something, and it's flat or going up. It's good. It is going up in the upper stratosphere, and this is near 40 kilometers. In the lower stratosphere, it's kind of more of a flattening out. It's hard to say it's really turned around yet. But these temperature changes are a response to the ozone.
We want to say hockey stick, is that a real one?
I don't know.
People use that phrase a lot.
Yeah. Okay, now I'm going to talk about the comparison. So that's the history of this interesting history of the SSU data, and it gives you a flavor of how much work. I mean, it's tens of people working for long periods of decades and comparing things and looking for little differences and trying to figure out those differences. It's an interesting problem. And again, same thing happens with radiosondes, trying to homogenize those time series. Okay, so now I'm going to show model results. So this is that model I talked about. And just a quick summary. It's specified SSTs, greenhouse gases, ODSs, and other things. And an important point here is that we have 5 realizations. And what I mean by that is this is run 5 times with the beginning initial conditions change just a little bit. And what that does is the natural variability is different among the 5 different runs. The forced variability is the same among the 5 different runs. So you can kind of see what's forced and what's natural variability. It's one way to separate those two. So what I've plotted on here is the global average temperature on pressure levels. And I have 5 lines overlaid. And the 5 lines are the 5 realizations. And the degree that the lines lay on top of each other is a signature of a forced response to the climate in the model. And the degree that their variability and wiggles in the data means that that's the component of natural variability in the response. So what you can see here is mostly on this time scale, this 40-year time scale, much of the variability is forced. And the forcing is such that so the troposphere is warming, but you can see these are ENSO events. And I'll show you in a minute. These ENSO events line up with the real ENSO events in the atmosphere, and that's because we specified the sea surface temperatures in the model. So the tropospheric temperatures, I didn't really appreciate this going into this work, but the troposphere is just a slave to the sea surface temperature. It's just, I've learned that.
Why is that?
I could have read the textbook, but I didn't.
Where do you stop feeling it though? Where does it stop feeling
Kind of the tropopause more. I mean, empirically, it's kind of the
Yeah.
tropopause.
Yeah.
So this is the QBO. This is 100 millibar. You can see this 2-year variability is this nudged QBO that's the same in all the models. You see that a little bit here. The volcanoes are quite good in this model, and it didn't used to be that way, and it's not that way in other models. So some models get very big warming or don't have any warming, but these are quite realistic. And if you like the solar cycle, you can see this. With your eye, you can see the cooling stratosphere. So this is the model on pressure levels. Now I'm going to compare. Oh, oops. I showed you this already. That's kind of what the structure looks like. Okay, but now I'm going to compare with the data. Okay, so this is now what we've done. We've taken the model and we sampled it like the satellites into this convolution with the weighting functions. There's 5 red curves, and they're sitting on top of 1 black curve. So the 1 black curve is the one I showed you 3 slides ago. It's our observations. And so this is kind of a thumbnail of how well does a model agree. And oh my gosh, it agrees really well is the answer. So part of this is prescribed. Oh, it's all prescribed, yes, but the troposphere is particularly prescribed, again, because the sea surface temperatures are specified. So you can actually see here that each of these ENSO events is tracked in the observations and the model, and that's, now I know this better, but that's built into the solution.
What's that last little anomaly, the red? It's not matching.
This is a problem in the model. Good eyes, this little bump here.
Yeah.
And we don't understand. I pointed this out to the modelers, and we still haven't figured out why.
Right.
And you would never notice it, right? And if you didn't have that black curve there to train your eye. But it really sticks out, and it's in all the realizations, and we can't figure it out. I thought it was a problem with the SST file in the model, and it's not. And we're still, don't know yet.
It'd be like a horse smelling the barn.
Could be.
The model knows it's getting to the end.
Could be. That's really good eye to pick that little detail out. And so the volcanoes are accurately simulated. This overall cooling, the solar cycle is well simulated. I think this is remarkable how well the model does. So what I want to talk now is about, I'm going to quantify what I'm going to call fingerprints. So I'm going to look at the structure of trends in a number of things. And trends, what we've done is kind of standard multiple linear regression, and we take out the QBO, or we include the QBO and ENSO variability and solar cycle. We don't fit the volcanoes, and we fit lines. Pretty straightforward.
You have volcanic aerosols, what other, is that the only aerosol that you have? You have just stratospheric sulfate aerosols.
There must be, I think there's a background sulfate aerosol there in this
But no
note.
troposphere,
Pollutants.
like no wildfires or anything.
I don't think there's variable tropospheric aerosols in this one.
There might be some that bleed into it through your SSTs.
Oh, yeah, yeah,
Right.
could be, yeah. Yeah. Okay, so this is, so we're doing that trend fit as a function of altitude for the global mean. And I'll show a couple figures like this, but it's got a continuous set of 5 red curves. So this is actually the fit, I'm sorry, the trends in the model at each model level, all the way. And the little black dots are the observations. And actually, there's a couple estimates of observations. I haven't talked about that in detail. There's 2 in the troposphere, and they lie right on top of each other. This is 2 of those groups, the star group and the RSS group. And then we have 2 in the stratosphere, and one is from what I showed you, the SSU plus MLS. The NOAA group have gone back since this time, and they've produced a different updated set of SSU using AMSU. And so this is a different independent data set from this data set, and so there's two points up here. They agree very well, is the short answer. And I've also, the red dot is the model, that red line sampled like the satellite. So that answers the trends agree very well. And you can kind of saw that from the last figure. You could guess here, yes, the trends are going to agree quite well. This quantifies that in terms of numbers.
Is that peak heating at 300 hectopascals, is there like a theoretical reason for that, or?
Yes, okay, so I said here, so the first fingerprint is this warming here and cooling here. Another fingerprint that people talk about and done some substantial work on is this increase with altitude, increased warming with altitude in the troposphere. And what this is it's if you have constant relative humidity, this is following a moist adiabat. You get more warming in the upper troposphere. And people have tried to figure this out from radiosonde data and from satellites. You can see kind of from satellites, it's not a very, because you're taking these big fat averages, it's really hard to say something about this vertical structure from satellites. It's also equally hard from radiosondes because this homogenization I talked about. How you do that homogenization influences what the structure of that curve is. But it's kind of an important fingerprint, and people have worked on it. I'd say the jury's still out on. And some people argued that our understanding of climate change is not right because we can't get this from data. But you can see the numbers are really small here. It's 0.2 K per decade. It's a really hard thing to measure. So we can't really do that, I don't think, with satellites very well. So this is the trends versus latitude. So this, again, just fitting a line for the whole 40 years almost. This is the warming troposphere channel, the cooling lower stratosphere channel, and the cooling middle stratosphere channel. So cooling increases with height here. The troposphere is warming. There's two observational lines on each curve, 5 red model curves. Overall, there's kind of reasonable agreement. But something interesting comes out of this is looking at the very large variability in polar regions. And what that is just, it's this natural climate variability. And I said here, a 36-year or 40-year data record is just not very long in high latitudes. There's so much variability. One model run will give you a trend that's here. A different model run, same forcing, gives you a trend that's up here. So it's really difficult. A corollary of that, it's really difficult to interpret our observational record. We have 40 years of data, that's all we have. And so to try to over-interpret what's going on at high latitudes, I think is a ill-posed question in some sense. So I personally, I learned a lot. The whole community does these ensembles now. It's a relatively new thing for the stratosphere, not so much anymore. But when I did this, it was like, oh my gosh, what am I doing wrong? I'm not doing it right somehow. This turns out to be a real effect.
Is it a little surprising that there's more variability in the southern winter for runs than the northern?
I guess maybe it could be.
Because in the
They all have
observations, there's more than.
They all have ozone holes. I mean, this cooling is fundamentally ozone hole, but there's in the model, and maybe in observation, there's as much variability in southern hemisphere spring as there is in northern hemisphere winter. It's really dynamic. Okay, so that's the annual average trends versus latitude. Kind of good, reasonable agreement, I think. But now I'm going to look at the troposphere channel, this MSU channel 2. This is really an interesting thing, I think. So I'm going to calculate the trends each month. And I want to look at the latitude versus months. Okay, this is a straightforward calculation. I just look at the January trends, look at the February trends, look at the March trends, and then contour them. And the idea is to look, is there an interesting pattern in this? People have been doing this type of map for the stratosphere for a long time, but do it for the troposphere, and I think it turns out to be very interesting. And kind of what you see is warming in the tropics and the whole northern hemisphere in the observations and the model. See, it's really interesting maximum. The strongest warming in the troposphere is not in the tropics. It's in the high latitudes in summertime. This is kind of an interesting new result to me. There's also warming in the observations in polar latitudes in wintertime. I'll show you in a minute. I think that's, well, let me show you. Hold that thought. But I think this is my fingerprint number 2, this latitude versus seasonal pattern of this warming in the troposphere. I think there's a high level of correlation between these two, and I think this is a fundamental fingerprint. There's no cooling, there's no warming south of about 40, 50 degrees south, or very, very little warming in either the ensemble or the MSU. And the reason is back to the SSTs that were imposed. So I dug this up from some other paper, but these are the trends in the Hadley SST data set that's input to the model. And you can see that the tropics are warming, as is well known, but the high latitudes are actually cooling in this SST data set. So this is the reason that we see this cooling in the high latitudes in the WACCM ensemble and probably in the observations.
I wonder how much of that might be just like the tail wagging the dog a little. You've got the warm phase of the AMO kicking in at around 40 to 60 degrees in the Atlantic, right? So
No, I'm not sure what you mean by the warm phase of the...
Are you looking at zonal?
These are zonal average,
yeah,
thick layer, 10 kilometer layer tropospheric temperatures.
right, but in the model driven by SSTs, right?
Right.
So it could be that you're entering this warm phase of the AMO where the sea surface temperatures are warming very dramatically in the northern Atlantic, and that's
Okay.
just bleeding into the entire zonal band.
Okay.
It's a possibility.
It could be.
Yeah, and that's about the right timing.
Are you
for-
talking about this feature here?
Oh, either one, really, yeah.
Or this one here?
Oh, no, the first one.
This guy?
Yeah,
Okay.
I don't know.
I'm gonna have one more slide on this, but I think this is not well understood at all, why this is. Just a note, if you look at the free running models, almost not, at least the NCAR models, and I'm not exactly an expert, but the plots I've looked at, the free running models do not have this cooling of the sea surface temperatures. The models like to warm the global surface temperatures. That's kind of...
Is there a trend in clouds, or is that hard to tell? Does anybody know?
I'm already beyond my expertise, and I'm on camera here, so I don't know.
You do have a different time period in this one, right? Starting at
A little bit,
1960
that's right, yeah, but,
versus
yeah.
around
Fair
1980,
enough,
so
that's right.
yeah.
But this just caught my eye of why there'd be cooling in the
Yeah.
model. Okay, so this gets back to this warming here. I just want to show this time series. So this is a time series of the anomalies kind of in a big box. And it's the box between 30 and 70 north and July to October. So it's kind of this whole big box here. The black line, there's actually two black lines on here, the two sets of observations, and the five model. And so you can clearly see the warming, but it's remarkable to me how much a slave atmospheric temperature is in the high latitudes in summer to the forcing, whatever the forcing is. A lot of this is ENSO variability. These peaks are ENSOs. This is a volcano here. This is Pinatubo. But the degree, or the lack of diversity among these forced models is remarkable. And I have not seen any suggestion of why this maximum warming is happening here.
So we would hope that in a year or so, again, you're seeing that anomaly at the top there where the models are going off the rails. You're hoping that that's going to go away when you fix the parameterization that's causing it, or maybe something that was introduced earlier on?
Well, when we figure out why it went off.
Yeah.
Yeah.
So it's a bug probably.
I think it's a bug. The modelers think there's a problem in my code. We've looked at the code a lot and we can't find the problem.
It's not clearly related to sea ice or anything?
It doesn't seem clearly related, simply related to the things we've looked at.
Kind of said over and over that the troposphere's a slave to the SSTs. And it looked like your SST forcing in the northern hemisphere the trend was fairly flat, and you're not picking up the polar warming.
Oh, polar warming is great. Great lead into my next slide. I'll skip a slide. So this is the polar warming. So now this is a different plot. Now, so this is now the trends over 70 to 90 north. So this is polar cap for each month. The black line, two black lines are a little bit different. And so this big warming here is that big warming there. Same result. And the 5 lines are the 5 WACCM. And now you can see great big variability among the models. So one interpretation is we just happen to have sampled a reality that looks, there's a model that's up here and a model that's up here. There's so much variability, we happen to have observed in our one observational record that type of behavior. Or it could be it's really a forced behavior, the model isn't capturing that forced behavior. I think I don't know what more you can say at this point.
Or maybe you need to do more ensembles to see.
I would love to have more ensembles, but it's only the stratosphere, and people don't want to waste their cycles on the stratosphere as much. We had to beg to get 5. Lorenzo Palmani told me we need 8.
But this is for the troposphere.
Pardon? This is the troposphere.
But so most tropospheric climate models get that polar warming. I mean, that's kind of a fundamental characteristic of the response.
It gets surface polar warming very clearly.
They don't integrate it?
I know less about
Okay.
about what all models get. I don't know.
You may be right, maybe it's not.
But this particular model, forced by observed SSTs, did not get it. And some do, and some do not. So this it's a cool lesson for me. It's like, oh my gosh, there's all this variability. And how do you interpret this observation? It's difficult. I skipped this one slide, I'm just going to show it. I went back to this slide. I'm aware of this, and we had done this work, and later after this work came along, Ben Santer published this really interesting paper. I ended up reviewing that paper. I loved the paper, I told him to publish it, and then they asked me to write this perspective, and I was like, oh my gosh, I have to do all this work. I was talking about this today. I had to do a month of work to figure out all the background on this, and I ended up doing it. But anyway, so this is the same similar diagnostic, but what Ben did was he looked at the amplitude of the seasonal cycle. So if you go back to this figure, this is happening in the summer, this warming. The most warming is happening in the summer when it's already warm. So this is a seasonal cycle, and the biggest warming is coming during the maximum part of the annual cycle. So you're making the seasonal cycle bigger. So Ben's work was looking And he's done a lot of this fingerprint work, kind of official fingerprint statistical tests of deriving firm statistical fingerprint signatures from the model. So he looked at the amplitude of the seasonal cycle. And this is what the observations show. So this is kind of similar to what my analysis I've shown before. So this says the amplitude of the annual cycle is getting bigger where it's red here in the northern hemisphere mid-latitudes. And that's because of that summertime warming. And this is what the models say. And he looked at all the CNEP5 models, and they're doing a similar thing. And it's very statistically robust. So he proposes this as a new kind of a fingerprint for the anthropogenic influence on temperatures. But I have to say, this is really not understood. And this is, I've been talking about this for a little bit, but I'm not clever enough to figure out why this is happening, but I think it's really robust. I somehow think it's related to the amount of water vapor. There's much more water vapor in the northern hemisphere than in the southern hemisphere, because the mean temperatures are warmer in the northern hemisphere. So I think, just as I said in the tropics, that amplification with height is due to the water vapor feedback. I think this may be also somehow related to the amount of water vapor. That's just a speculation. And I'm going to quit. I had a little bit on more, but I'm going to quit. You see everything. I'm going to stop. So in my summary, this tropospheric warming and stratospheric cooling, increasing with height, the fundamental fingerprint, we really understand that. And I think that's, people argue, is there really anthropogenic climate change? And I think they have to, or it's due to some other reason. I think this signature of stratospheric cooling is a slam dunk, I think, for me. This warming in the troposphere we've just been talking about, it's a fingerprint. I don't think it's understood. I wish I could explain it. I can't. And in the stratospheric temperature evolution in response to ozone, I didn't really show it, but the model captures this really well. It cools about twice as strong during the ozone depletion and about half as strong after ozone recovery. The model simulations are in excellent agreement for all these things. I didn't show you, and so I haven't shown you solar cycle, but if I did all these signals, it's remarkable to me. And there's almost no interesting differences. Part of the cool thing of doing this, at the end, you like to see some differences, and you go explore and figure out we can make the model better. There's like no interesting differences here. Good for the modelers, but less interesting for me or something. But I should say, but these are these forced SST runs. And one interesting difference, if you look at the free running models, they're all warming faster than the observations. And that's an outstanding question. Why the climate sensitivity of models is much higher than our one observational realization.
So those free running models, the sea surface temperatures are getting too warm too fast?
Yes. And hence the troposphere temperatures.
Okay.
And some models get much too warm compared to observations, and some get less warm. But even CESM run in a free running model warms faster than the simulations I showed.
Are you seeing any reductions in the thermal circulation or anything?
You know, I don't. I'm sure the
Yeah.
climate guys are studying that, but
Yeah.
that's not me.
Just,
I don't know.
It'd be interesting to figure that out.
And actually, this ensembles, this is kind of new to me looking at ensembles, but it's really interesting to quantify the internal variability. And anybody does this know that in the troposphere community, they run 100 ensembles of things nowadays and try to deduce what is forced and what's natural variability. A lot of the observations or a lot of the climate system has a lot of natural variability, a lot of low frequency variability. So separating things is a very difficult problem. In the stratosphere, there's really big variability in the polar regions. And 40 years is all we have in the stratosphere, or 50 years, if you look at it. It's a short record. And talk to somebody, the scientists need to be older, live to be 30 years older or something to see a stronger conversation. Anyway, I'm going to quit there, and thank you for lots of good questions.
Do you like the field questions? Or?
I'm happy to. We've had lots of questions, but I'm happy to have more.
Have you looked, so your 5 members at the high latitudes in the troposphere, have you looked at whether like midwinter warmings occurred? Yeah, that one. Oh,
Wait, this is not something.
There, right
Oh, there we
there.
go, yeah, there we go.
have you looked at whether
I
there was
don't-
midwinter warnings?
No, I haven't.
In
No.
those two?
No, no.
I bet.
But this is troposphere, but that's a
I
good
don't know,
question.
But again, I think you get a change, a long-term change in the troposphere.
Very good question.
In response to.
I haven't looked. And that'd be a case, you'd really like to have 20 ensembles,
Right.
or a larger number than 5.
Or even, and you look at high latitudes in the southern hemisphere, you know, there's a lot you're not capturing there as well. And that's the other place where you have a whole lot of variability in the stratosphere.
Right.
Yeah, I had another question, but as long as that's up, what I was suggesting before that I think you could answer pretty easily by recreating that plot, and the idea of the tail wagging the dog is that that Atlantic multi-decadal variability is very strong in the summertime at those higher latitudes,
Okay.
I think. Michael could correct me if I'm wrong on that, but I think it's fairly strong. And the years that you're looking at have mostly a very, very strong positive trend on it. So if
Let me go back to this picture.
yeah, okay. So if you were to just, instead of doing a complete zonal band, just do like from 260 to 350 or something, you might be able to determine whether that's driven almost entirely by the Atlantic.
Well, this is a little bit from Ben Sanders' picture, so this is kind of related, it's not exactly the same calculation,
Mhm.
but the largest warming is kind of on the eastern side, or over the
Right.
continent.
But if that was SSTs, well, okay, I'll have to think about that. We certainly get pretty strong warming, but it'd be a little bit to the east of where that bullseye is over Newfoundland. But, yeah, just in the sea surface temperature. I have an infinitely more important question for you.
Okay. What's for dinner?
All right. I think of things in terms of how it might affect hurricanes. It's just the way I see the world. But the way that the heating profile is driven by CO2 forcing, you know, the warming in the troposphere and the cooling in the stratosphere, is there a lot of seasonality to that? I mean, does that crossover point at 0 lower in the summer, or? You see where I'm going with this,
I
right?
do see where you're going. I think there's enough wiggle room in all of these. I didn't have any uncertainties on here, but there's statistical uncertainties. Exactly where that crossover is where you want to, is there a seasonal variation in that crossover? I think
Yeah.
not to first order.
Uh-huh.
Let me show you in my extra slide deck. Here, so this is, I've shown you this. This is a similar figure for the lower stratosphere channel. And there's not much seasonality
Hmm.
in either observations or in the model, nor in the troposphere. And so in order for your question, in order for there to be a strong seasonal cycle, you would expect to see some
Right.
signal here.
Well, either in the lower levels or in the SSU stuff in the upper levels, either one would do the trick.
Yeah, but MSU, I think there's not. I mean, if,
Uh-huh.
it's really lower stratosphere where you want to kind of compare that.
Okay.
In fact, here's a more relevant. This is that same picture, but it's in the deep tropics now. So this amplification is stronger in the tropics.
Mhm.
But that comparison I showed you is this channel versus this channel.
Mhm. Okay.
So there's not a big seasonality.
If I could ask a question, a lot of people are really interested in future changes in the jet stream locations and strength. But I feel kind of confused about different results, that some models seem to suggest different scenarios. And is it possible, given the strength of this temperature signal, to have a little bit more certainty about what's happening with the winds, or is that, how would you characterize the shift in winds?
I would
Is
ask
that hard to?
I would ask somebody who knows more than me, so I would do it, because I don't know very much. There's subtle changes in.
Maybe taller? I was thinking of your latitude height section of.
Yeah, I mean,
There's a little.
the subtropics, they should stick up higher in the subtropics, because you get warming in the tropics and cooling in higher latitudes. So thermal wind, the jets just stick up a little bit more. But as far as shifting, I think there's a
I guess I
substantial
should
debate.
read Butchart et al. 2008, is that right?
That's one thing, but I mean, it's more the widening of the Hadley cell, that question. There's a whole community, more people that are in this room looking at why is the Hadley cell widening? It's a very wave-mean flow interaction, very complicated problem. I can't answer it. It's a simple answer.
I'm guessing, is it, like, there's the northward shift in the storm track idea versus kind of the changes in the upper level shear, more on like the troposphere, or on the equatorward side of the jet and the subtropical jet, that maybe, I think people sometimes look at the eddy-driven jet and they have a specific criteria for that, and that doesn't capture all the same changes in the subtropical jet.
Yeah, it seems like there's changes in the surface temperature gradient, changes in the temperature gradient in the troposphere, and then in the stratosphere it's separate. But maybe they all would create a
But they're
coherent
small,
picture
it's
there.
really hard to, my take is that it's really hard to diagnose because they're really small changes, there's all these feedbacks. I saw a talk by Lorenzo Palmani recently where they took the 4 times CO2 and really hit it, and then you can diagnose some of these changes. And even then, they're relatively small changes, but to try to do it with the current climate model, I think is a hard problem.
Any other questions? All right, well, let's thank you.
Thank you all.